now? Okay. Okay. Hello, everyone. My name is Federico. I'll be presenting our work. This is joint work with Feargus, Pendlebury, Fabio, Pierazzi, and Lorenzo, Cavallaro, our wonderful collaborators, and it's so great to be here today. So we all know the story of machine learning's effectiveness. Machine learning has dominated in tasks ranging from image classification to neural machine translation. And while machine learning has shown very promising results, there still seems to be something missing when it comes to malware classification. So you may ask, Federico, what's taking so long? Well, this all stems from the fact that while other domains treat adversarial attacks as some kind of special edge case, this is absolutely not the case in security. Actually, a detection system is essentially worthless if it's not robust to adversarial behavior. So whenever we deploy this new detection system, this triggers an immediate response from the adversaries, and this is a nightmare for machine learning practitioners. In particular, this is because it leads to a variety of dataset shifts, which are usually umbrella termed under concept drift, but they can be much more nuanced than that. And this is a nightmare because it's violating one of the main assumptions which we're making when training machine learning systems, that the train and testing data are IAD. So this is exactly what our lab was trying to address in 2017, work which was published at ICSI Security in Transcend. So when we have a regular classifier, we take a new example, and then we pass it to a classifier, get our classification. Instead, in Transcend, we add two components to this system. So we first add a conformal evaluator, which is responsible for assigning some sort of quality measure. And then this quality measure is then passed on to Transcend itself, which is our calibration mechanism. So Transcend will have some kind of thresholding, some kind of thresholds for each class, and then based on these thresholds, Transcend will decide whether to accept or reject a specific classification. This is known as classification with rejection in the machine learning literature. So Transcend performed very well, but we thought we could address some of the limitations. So this is in particular what we try to address. So first of all, we propose some kind of important theoretical missing link between conformal evaluation and its underlying statistical theory, which is conformal prediction. And we use this link to kind of motivate why conformal evaluators work so well in the first place. On top of this, we wanted to make Transcend scalable to real-world data sets. So using this missing link, we propose new, sound, and flexible conformal evaluators, and we also improve the thresholding. We make that faster. So to evaluate this, we evaluate this on a wide range of malware domains and on a wide range of classifiers to show how kind of general this technique is. And maybe let's go a bit into, let's try to get a bit of a deeper intuition into conformal evaluation, and let's start by talking about conformal prediction. So conformal prediction is what lays the ground for conformal evaluation. In a typical operation, a conformal predictor will output a prediction set. So this is a bit strange in terms of machine learning because we're usually outputting some kind of classification. Here we output a set which contains a true label with a likelihood 1 minus epsilon, with some level of confidence. And these strong results only occur when we have two core assumptions. So that of exchangeability, which is some kind of generalization of IAD, and the closed role assumption. If we train on cats and dogs, we're not expecting parrots in the test set or random noise. So this is all based on a scary term called a nonconformity measure, but it's actually quite straightforward what a nonconformity measure is. A nonconformity measure measures how dissimilar a point is with respect to other points of the same class. Now, this is classifier agnostic. We can build these for many different types of classifiers, so let's have a look at a few examples. Now, the blue region highlights all the points which are less similar than the red testing point with respect to the black class. So this is induced depending on the black class, and this is induced by the NCM choice which we make. So to quantify this relative dissimilarity, we construct a p-value, and this is simply the ratio of points in the blue region with respect to the ratio of points in the white region for the black class, and then we flip that for the white class. And we do this for every class in our task. So for example, for classifying malware, we would have a p-value for the malware class and a p-value for the benign class. Now, hang in now with me, because this is really kind of the core observation, the fact that these prediction regions so here we're still sticking to conform prediction, and we'll link this to conform evaluation. Now, these prediction regions are based on the significant level epsilon. And actually, we can imagine these as being stacked such that the higher the confidence level, the more labels will be present. And we have these two edge cases. So the first edge case is when epsilon is 0, so our likelihood will be 1. And here we're saying, give us a set with likelihood 1 that contains a true test label. And this is going to be trivially the entire training label space because we're saying, by the closed role assumption, this is like the only solution. So if we jump over to the other side, we have the case where we have a likelihood of 0. And again, here we're kind of violating the closed role assumption, and so we will output the empty set. So also important is this region which only contains 1 point. This is sandwiched by the credibility and confidence. And in particular, it's this credibility that gives us the connection between conform prediction and conform evaluation. So here, Tom the cat has this cool idea. So a low credibility means a high probability of an impossible result, because again, we're directly violating the assumptions we set off with. And this means that, well, how could we explain this? This is because the distributions are shifting. And this is the fundamental difference between conform prediction and conform evaluation. Whereas conform predictors predict given this prediction region, conform evaluators evaluate predictions of the underlying classifier, borrowing tools from conformal prediction. So let's have a look at our thresholding mechanism, Transcend. And Transcend tries to answer the question, at what point should we actually do something about drift? At what point should we actually reject points? So to do this, we hold out some kind of calibration set, and we can imagine that we run our classifier in this calibration set, and we can partition the data based on class and based on whether the classification was correct or incorrect. Now, what we then do is generate our thresholds for each class. And these thresholds are generated on some kind of optimization constraint which we try to solve. And it could be, for example, find the best thresholds which maximize the F1 score given some kind of rejection rate. These parameters we can tweak depending on what we want to do. So Transcend is effectively trying to maximize the separation between the credibility of correct and incorrect decisions for each class. Now that we've calibrated Transcend, at test time, all we simply need to do is sweep the point through the classifier to get the classification, and then compute the credibility of that classification given that it's of that class, and then we compare to that same class threshold. So if the credibility is above the threshold, we deem this as a credible classification, so we can trust it, and instead if it's below the threshold, we reject it. And once we reject it, we can really do what we want. We could manually inspect it or have a look at many other different things. So now let's have a look at conform evaluators. Conform evaluators have many different structures. First of all, we have the transductive conform evaluator. So the transductive conform evaluator it works in a kind of leave one out fashion. So we have this. So we target the p-value computation singling out a point. So for a single point, we train on n-1 points and compute the p-value for that point we're targeting. Now, you can imagine this leave one out fashion, we have to train n classifiers, and really nobody has time for that. The advantage of this technique is that this is rooted in conformal prediction theory, so it's actually a sound approach. The disadvantage is that this is computation infeasible for large data sets. So one kind of thing we can try is, instead of doing a leave one out approach, is we could do this in batches, and here we get approximate transductive conform evaluation. So this is an attempt at trying to make transductive conform evaluation actually feasible in practice. So here we could do like a k-fold, where instead of n points we train 10 classifiers. So the p-values are not computed in batches, but importantly, this relies on an unsound assumption. The fact that when we do it in batches, we're in some way shifting the decision boundary of the classifier, which is then used to compute the nonconformity measure. So this approximation is only as good as the approximation of the decision boundary is. Now, this was kind of unsatisfying because we really wanted to have a statistically sound approach. And this is what we then introduced to try to remedy this. And this is an inductive conform evaluator. And here the advantage is that we're only training one classifier. So this is really like practical. what we do is we split the training set into a true training set and then a calibration set. So we train on the training set and then calibrate and then compute the p-values in a leave one out fashion, but only in the calibration set. And this is rooted in conformal prediction theory, and importantly, it's computationally very efficient. There is one drawback to this, however, is the fact that this is informationally inefficient because we're throwing away all that gray region. So we wanted to address this as well, and to do this, we proposed the cross-conform evaluator. You can think of this as having an ensemble of inductive conform evaluators acting in parallel, and they act over some kind of majority voting. So this is rooted in CP theory, so it's a statistically sound approach, and it's computationally more efficient than transductive conform evaluation. Obviously, this is less efficient than inductive conform evaluation, but it's trivially parallelizable, so if you have the resources, it would take the same amount of time in practice. And the advantage is that we gain the informational efficiency back as we can now compute statistical support over the entire training data set. So here's the experimental setup. We have Android experiments with Rebin over a 5-year time span with a linear support vector machine. We have experiments on Windows PE with the Ember v2 dataset with gradient boosted decision trees. We have experiments on PDF malware with HEDOS. This is a feature space which is robust to drift, and we use random forest. We will be focusing on the Android experiments in these slides. And then we have our thresholding optimization constraints. So we operate over a specific rejection rate, and we operate over trying to maximize F1 score. Now, these can be tweaked depending on what the practitioner wants to do, for example. Also, these constraints will only be satisfied at calibration phase, because as we are at test phase, we would actually expect more rejection as there's more and more drift. So here are the results. So just to interpret these slides, the middle dashed gray line is the baseline performance. So we're training on 1 year and testing over 4. We can see that the baseline performance deteriorates, and this is due to the drift in the data set. And then we have the top blue line, which is the F1 score of the kept elements that Transcend decides to keep, and the F1 score of the rejected elements is in red. So we'd want the blue line to be close to 1 and the rejected line to be close to 0. This would mean that Transcend is accepting correct classifications and rejecting incorrect classifications. We also have the histogram of the quarantined elements. So that's the rejection rate at each month. We can see that the rejection rate increases as time goes on. Transcend is correctly identifying that there's more drift occurring as time goes on. Now, we can compare this with inductive conform evaluation, and we can see how these two techniques perform extremely similarly, but we can look at the CPU hours of the two techniques. ICSI takes 11 hours, while approximate DC takes 46. So we get a massive computational speed up, and for a relatively, extremely similar performance. And here, there's the performance of CCE. Now, CCE is an ensemble, so we expect this to be kind of more confident, and we can see that the kept F1 score is pretty much almost always at 1. But this is at the sacrifice of we're rejecting more points, and we're also making a few more mistakes. We can see that the red rejected line is not at 0 anymore. So we're rejecting more points, but at the same time, this is useful if we want a very confident kind of classifying ensemble. So now, you may tell me, okay, Federico, this is very cool, but we already have probabilities built into the classifier, so why don't we just use those? Well, let's have a look. So the top row is what I just showed you before, and we can compare them with just using the built-in probabilities of the classifier. So here is the results for the probabilities of the classifier. Now, what we see is that it seems kind of all over the place. So when there's less drift towards the start, the probabilities tend to perform still worse than conform evaluation, but do not seem as terrible. But then as time goes on and there's more and more drift, these probabilities make less and less sense. And this actually makes a lot of sense because probabilities make the assumption that the training and testing data are IAD. So probabilities as the data sets drift more and more actually become you should trust them less and less. So for this reason, we see that conform evaluation actually gives a lot more statistical support when just using probabilities. And to conclude, we presented insights into conform evaluation theory by giving a missing link between conformal prediction and conform evaluation. We also presented novel evaluators in the inductive conform evaluators and in cross-conform evaluators. In the paper, there's also operational guidance for deploying Transcend, and again, one of the main goals of this paper was to show that Transcend is actually scalable in practice. It's also important to mention that cross-conform or conform evaluation and transcend can actually be decoupled. So you don't need to necessarily have a conform evaluator in a pipeline with a classification with rejection. You can, for example, use a conform evaluator for uncertainty sampling to get like better scores when samples are drifting and explore points which have less statistical support. So we also have the code available at the project page, and you can check out our paper and then the original transcend paper as well if you'd like. Thanks a lot.
Do we have any questions for Federico? Yes.
I have a quick question. So as you pointed out, concept derp is not really adversarial attack. So under adversarial attack and adversarial setting, which is securities, how does these techniques perform?
Yeah, so we've been thinking a lot about this problem at our lab, and there seems to be a connection between the two. Now, in our evaluation, we're simply looking at drift, but yeah, it's definitely very related. But again, we can make no claims with regards to the experiments we ran with this work.
And I was wondering if you could speak a little bit to the trade-offs that exist between models that are just robust in their feature selection to concept drift, or
yeah. So actually, I do have some backup slides, and this is the results for HEDOST. So HEDOST is, I guess the models are not inherently robust, but the feature space is robust in these experiments. So we can see that when we have a robust feature space, if we look at the gray baseline, there's very much like a lot less drift in there. And so when we use probabilities seem to work actually like quite well. And this is because, again, probabilities work fine as long as you're not having a lot of drift. But we can see that even conform evaluators seem to beat probabilities even in this case. Again, it's like they're probably quite similar in this scenario, but yeah, obviously conform evaluation is designed for high drifting kind of situations.
Awesome. All right. If there are no more questions, thanks, Federico.
Thank you.